Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, ladies and gentlemen. I suspect we're going to have more people come, but I'm going to start the session. So I'm Judith Bishop, Director of Computer Science here at Microsoft, and it's my pleasure to introduce this session, which is on large-scale debugging. We have three speakers, and the first one is Ben Liblet from the University of Wisconsin in Madison. And apart from doing all the wonderful things in academia, he has also done two other things, which is to spend quite a lot of time in industry. And he also won the ACM Distinguished Dissertation Prize at one point in his life. And now he's going to tell us about his cooperative debugging. Thank you very much.
Thank you. Hi, everybody. My main interest in software is what happens with that software the day after you release it to the users. I'm interested in studying software in its natural environment. And this natural environment is really, really important because I don't care how many testers you've got. The users have you vastly outnumbered. There's an estimated 1 million runs of Microsoft Word every hour. How many testers does Microsoft employ? I don't know, but I bet they can't beat a test rate of 1 million runs every hour. And there was a study, I think this was actually back in 2002, that showed that 1% of software errors cause half of the crashes that we're seeing out in the field. So the users really know what's important. What's important is whatever's important to those users. Now, there are many different reasons why you might be interested in understanding the behavior of software in its natural deployed environment. In this talk, we're going to focus on just one motivation for that, and that is post-deployment debugging. Finding all of the bugs that your talented but limited QA team missed before the day of the release. Our approach to this, if any of you are not familiar with statistical debugging, I'll give you a little bit of background on that, and then we'll get into some of the more recent work. Our approach is to collect feedback data from the field, and then mine that using methods borrowed from machine learning to find likely causes for the bugs that are happening to those users. This is an empirical approach to bug hunting. It is an approximate approach. We're not doing static analysis. We're not proving that the program must not exhibit a certain kind of bug. Rather, we're trying to find out what's going wrong in the field and what can we do to help developers fix that. Now, the overall picture of cooperative bug isolation looks like what we've got here. I'll take you through different parts of this picture in stages. In this talk, we're mostly going to be focusing on the bottom part of this diagram, where we get feedback back from the users and then mine that to find top bugs with their likely causes. For now, the thing I want you to focus on is the fact that this is a loop. It is a cycle, and the users are part of that cycle. Every time we go around this cycle, the users are helping us understand how the software is failing and what we can do to make it better for them. We're going to start out with finding out what the data is that we're going to collect in the first place, what I would call predicates. Your decisions about what to instrument when you release the code affect the kind of data you get back later. What I've marked here is counts plus happy or sad face. Think of that as a label marking each run as a success or a failure. So deciding what's interesting then determines the feedback that we will get from the users later on. So what's interesting? What could help us find a bug? Well, how many of you are C programmers? Or have done some C programming? OK, fairly big number. How many of you know that fprintf returns a value? How many of you know what that value means? How many of you check it? Like ever? Right. I'm just as bad as you are. So fprintf does return a result, and that result might be informative. That result might tell us whether some operation has succeeded or failed. So what we're going to do is we're going to systematically, automatically, inject instrumentation that will give us some information about how fprintf behaved. In particular, we're going to count how often it returned a -0 or positive value, because in C, returning -0 or positive is often used as some sort of success or failure indicator. We're going to do this systematically everywhere we see a function call in the program. We're not going to get tired of putting this in because it's being done automatically. So the instrumenter can be much more systematic than any human programmer could be expected to be. And that's just one example of something that might be interesting enough to monitor post-deployment. Many other things could be interesting. Branch directions, weird floating point numbers, reference counting behavior. Anything you've got in your head that you think maybe could be related to a bug is worth instrumenting. This is not the time to be stingy with your instrumentation. If you think it could be interesting, let's instrument it, and we'll find out later. What we get back from this is well, you can think of us making a stream of observations about the program's behavior. We're actually going to flatten that down to just a count, as we saw with the fprintf example. So we'll count, say, how often a branch goes left versus right. We'll count how often a division leads us to -infinity, and so on. We do some very sparse sampling of this data. Our primary motivation for that was performance. By sampling at a rate of, say, 1 in 100 or 1 in 1,000, we're able to exploit the 99 in 100 case as a fast path. So we pay performance that's actually much closer to the original uninstrumented code. I'm not going to talk in detail about the compiler mechanics behind how we take advantage of the sparse sampling for performance. It also, by the way, is valuable from a privacy standpoint. I don't learn very much about you from one run. 99% of what you do, I don't even see. But over the course of many runs, we get this sort of feedback report that tells us about what the software is doing in the real world. We get this vector of counts of the different things that we were observing, how often they occurred. And we get an outcome label telling us whether that observed behavior should be considered as an example of correct behavior or should be considered as an example of incorrect behavior. So now we're down in the bottom part of this loop. We're getting this feedback data. And you can imagine the runs being split into two piles. We have the good pile and the bad pile. And you look at the two piles and you want to figure out what's different between them. Now that's easy enough to do on a small scale. We're talking about 900,000, a million, many different instrumentation points. So we need to use some tools to help us find the difference between good and bad. The kind of feedback that we're going to present to developers might look something like this. This is the feedback produced by one of our statistical models. In this particular case, we instrumented over 850,000 potentially interesting points, among which we found 3 bug predictors. That is, 3 behaviors that are predictive of failure. Now, I've omitted here the more detailed information that we present, which includes things like file name, function, line number. We're really pointing you to a specific behavior at a particular line of code that is associated with failure. Those colored bars you see are actually a summary of quite a few different metrics that we collect. The important thing to know here is that a wide bar filled with red corresponds to a common bug for which this is a very strong predictor of failure. In this particular case, each of these 3 predicates was genuinely a predictor of a distinct bug. We isolated 3 previously unreported bugs, and these have all been confirmed as real bugs by the developers. Now, how do we get this out of 150,000 or even 500,000, 900,000 instrumentation points? How do we find the 3 that matter? This is where I take off my compiler hat and I put on my machine learning hat. Because the data is very sparsely sampled, this turns into a statistical modeling problem. What are the behaviors that are correlated with success or failure? We've developed a number of different models over the years to answer that question. This is one of our more recent and probably our most mathematically sophisticated. It's a variation on something called LDA. This is delta LDA. I'm going to take you through this formula in great detail. No, not really. I only understand about a quarter of the mathematics that's in here. This is why I collaborate with very smart machine learning people. But I can give you at least a sort of pictorial version of what delta LDA is about. LDA, latent Dirichlet allocation, is a process of taking a set of documents and modeling each document as a mixture of different topics. So maybe this document is 75% politics and 25% sports. because it's talking about the World Cup or something like that. So a document is a mixture of topics. As applied to bug hunting, a document is a run. A topic is some usage pattern. Now, most of the usage patterns exhibited by a piece of software are perfectly fine. Most of what a piece of software does is not buggy. But there may be some small collection of behaviors that are only exhibited by the failing runs. And that's what we're interested in. So we're actually trying to isolate some very rare topics, the buggy topics, from among these much more common usage patterns. If we imagine that these runs here, or that these images here represent the original runs, the items to the left of that bar are the successful runs. And those are the most common. The items to the right are the failing runs, and they certainly exhibit different behavior. Now, if we actually run literally these little bitmap images through our analysis, traditional LDA would give us a result something like that. And what you can see here is that the successful examples are so much more common than the failures that the failures essentially get wiped out as noise. You end up with a model that really only describes the successful behavior of the program. But that's exactly what I'm not interested in. I don't care about what's good in the program. I care about what's bad. What delta LDA does, the delta in delta LDA, is that we can reserve some part of the feature space, some part of the dimension space of the LDA model for the exclusive use of failing runs. Imagine that there is a reserved seating area, and only the failing runs are able to draw upon that reserved set of topics. When we use that to model these inputs, we end up with something that looks much more like the original. And you can see that the failure topics to the right of that red line really do capture what is distinctive about the failing examples that we started with. Now, when we apply a model like this, we do get a list of predictors, a list of things that go wrong when the program fails. And that's good as far as it goes. It's good to a point. A single predictor, like this branch went left, partitions the runs into two subsets, the ones where that predictor was true and the ones where it was not. So we're taking the space of all the runs and we're drawing a line down it, separating it into two subspaces. That works great if that is enough to describe the difference between success and failure. If you have a simple bug, then a simple line will separate good from bad. However, some bugs are just more complex. For some bugs, a simple straight line is not enough. We need something that has more subtlety to it. We need something more than simply a linear separator between these two spaces. If we have a more complex bug, we need a more complex language of describing the difference between good and bad. For example, a bad pointer error. This is a little fragment of code from the same program that I showed you analysis results from earlier. If O plus S is bigger than buff size, if that branch up top there is true, then the function we're in returns early. It's sort of an early escape. If that happens, then this malloc call later never occurs. And the pointer provided by that allocation is never stored inside of this entries.data data structure. So that .data field is junk. That does not by itself cause failure. What causes failure is if you subsequently use that junk pointer. So two things need to happen. We need to have a pointer whose value is junk, and we need to have a subsequent use of that pointer. Those two together, that is, the conjunction of those two, causes failure. So we're really interested in forming more complex predicates, conjunctions and disjunctions of simpler observations. Now, even if we're not going to actually instrument all pairs, all conjunctions and all disjunctions, even inferring those predicates offline is prohibitively expensive. There's simply too many pairings. Just with two predicates, we have a quadratic blowup. If you try to do more, then of course it grows even more rapidly. In one experiment that we did with 500 predicates, which is quite modest, and 5,000 runs, it took 20 minutes just to consider the possible conjunctions and disjunctions of pairs of predicates. So we need some way to be smarter. We can't just brute force this. We need to focus our attention on something that's more likely to yield fruit. We have two ways of doing that. Firstly, we found in practice that conjunctions and disjunctions that were very widely separated in the program were unlikely to be useful. And even if they were strong predictors of failure, it was very difficult for programmers to even understand what they meant. So we imposed a admittedly somewhat arbitrary cutoff that we found to be very useful in practice of 5%. I can go into a little more detail about how we measure that distance, but the important idea here is that we have a sort of distance metric between two predicates, and we have a cutoff at 5%. So we want predicates to be close enough to each other to be relatable. Secondly, every one of these predicates has a score associated with it, and the predictors that we show are sort of the top scoring predictors. Before we compute the actual score of a conjunction or disjunction, we can estimate what the best possible score could be based on what we already know about the simple predicates. If that score, the best score we could possibly get, is still smaller than the score of the individual components, then Y form the more complex predicate. If A and B is no more informative than just A, then keep it simple. Just stick with A. So we're able to perform this sort of bounding check and throw away a lot of junk that could not possibly give us a better result. What this does is this allows us to estimate those scores at a cost that is constant per predicate pairing without having to do a linear scan over all the runs. Things that survive that filtering pass, we will do a linear scan across the runs to see if it's really worth keeping. But in constant time, we're able to just discard a lot of junk. When we applied this to the Siemens suite, which I realize is a somewhat passé benchmark suite at this point, it was more hip at the time we did this research. We found the following mix of predicates. Now this is rather dark, but the green bars, those represent variations of these different buggy programs in which a conjunction turned out to be the most useful predictor. One very nice quality of our statistical models is that we allow many different possible bug predictors to compete. The more bug predictors you've got, the better. Just put them all in the pot, we'll stir it around and see what floats to the top. What we're showing here is that overall, almost 90% of the time, a conjunction turned out to be the most accurate bug predictor. So it really is the case that a more complex boundary between successful and failing runs is truly useful. Now you're probably noticing the one exception there, schedule. The issue with schedule is that there's a point where you're supposed to have a priority number between 0 and 3. The bugs in schedule involve checking that bound incorrectly. Schedule will fail if the priority number is smaller than 0 or bigger than 3. And so what we see here is that is accurately captured by a disjunction, just as you would expect. In terms of the effectiveness, we're able to throw out about half of the predicates just because they're too far apart. Another 10 to 20% we prune out using this score check. The compute but discard bar, that sort of dark blue bar, that's where we wasted effort, where we computed the exact score and we decided that we didn't like it, we threw it out anyway. Overall, the effect of this is actually quite large. Although it may seem small there, reducing the number of predicates has follow-on benefits further on in the analysis, so that 20-minute time I quoted earlier shrinks down to just a single minute. And we still get exactly the same results that we would have gotten if we'd considered all of those within radius predicate pairs. So now I want to tell you a little bit about how we put these predictors in context. And the real focus here is helping the developer understand what these predictors mean in the context of their code so that they can fix that. Now, part of putting it in context is simply having a good user interface. And there was a project that I did with some folks in Microsoft Research where we've actually integrated one of our statistical debugging models into Visual Studio. You can download this. It's a free download for Visual Studio 2010. It works on any .NET targeted language for which you've got a test case. You run the test case, you get a visualization at the bottom. You can see again those red bars. And then you can click through on any one of these to see what's going on in your program. Holmes Instruments program paths. So when we focus on one of the paths in this list, we get a view of the source code in which the statements along that path are highlighted. We find that this really helps developers understand what's going wrong in their code. Very briefly, I want to tell you about something else we're doing here to put predictors into a more informative context. The style of instrumentation I described previously is really hunting bugs with a shotgun. You're shooting massive amounts of instrumentation all over the place, hoping you hit something. What we're doing now is trying to focus on being more selective. We instrument just some tiny fraction of the program, and then based on the feedback we get, based on the initial information that's coming back, we decide where we should move our instrumentation to in order to bring it closer and closer to the points of failure. Because the fact is, most of what the program does is correct. Almost anything you instrument is not a bug predictor. And if we're able to be more selective, then we can reduce the overhead significantly. I'm not going to be able to go through the details of how we do that. In brief, it is an iterative search through the control dependence graph of the program. We have some region of the code that has already been instrumented. And based on that, we decide where to expand our frontier. What is the most interesting part of the program that we have not yet seen in detail? In machine learning terms, we would describe this as a form of active learning, where you get to choose your next experiment in order to maximally add to your knowledge of the system's behavior. The results of this are that we find we explore about 9% of the program on average. That is, we get bug predictors that are identical to what we would have had from complete instrumentation, yet the entire process only explores 9% of the program. In this case, we're using much more realistic pieces of software, GCC, Bash, and so on. We do a sort of adaptive process, adaptive iteration, as we move the instrumented points around, and we find we need tens to hundreds of those rounds. That's not really much of a price to pay when you've got 1 million users every hour helping you find bugs. And the performance impact is very dramatic. If we're doing exhaustive instrumentation as we'd done before, and cranked the sparsity down so low that we're really barely measuring anything at all, we still would find that we were getting 10, 20, even up to 50 or 60% overhead. Binary instrumentation is much, much worse. 3x slowdown, simply because a binary instrumenter doesn't have the luxury of doing extensive optimization of the instrumentation it's put in. But when we move to our adaptive approach, we are so lightweight, there's simply so little that we're doing on any single round that the overheads we're introducing are less than 1% on these very large programs. I'll give you a sneak preview of a paper that we've got coming out at Uppsala in October. And in this, we're applying some of these statistical ideas to finding concurrency bugs. The raw data here is in the form of different thread interactions. Whether a pair of accesses are atomic or not, whether a function is called reentrantly or not, the sorts of things that could be informative. Again, we've got that very low overhead because we're doing the sampling very sparsely. And we find that we've got actually this really great data source now, all sorts of interesting things that we can mine out of this thread interaction data. We know that we can find crashes, races, atomicity violations, other sorts of concurrency-related bugs. One thing that we kind of get for free, and I have to admit I didn't even think of it ahead of time, but when we saw it, it's plain as the nose on your face, is that we are looking for correlations with failure, which means if you've got a benign race that doesn't cause failure, I don't even see it. I don't have to go through all kinds of hoops to ignore benign races. I don't even notice benign races because benign races don't correlate with failure. So it's in that sense, it's sort of black box driven. All I care about is what causes failure. If that race condition isn't causing a failure, then it's nowhere on my radar. So what we've learned from this is that there's, this is a session on large-scale debugging, right? Data-driven software engineering. There's a huge, huge data source out there. And now we finally have the ability to tap into that. The users are not waiting for us to fix all the bugs. They will be running this code whether it's buggy or not. If we can tap into even a small part of this, then there's a massive amount of information waiting for us to get our teeth into it. I think also I'd like to make a case for there being great potential in hybrid approaches, in crossing the boundaries that often separate our discipline. The dynamic style allows us to connect the debugging efforts to reality. We really are connected to the actual field behavior of the software. These statistical methods, which were really an eye-opener for me, coming from more of a static analysis background, have this remarkable power to give you some kind of vaguely a correct answer, even in the face of terribly incomplete data. They may be uncertain, but they can always give you some sort of best guess, even in the face of uncertainty. That's extremely powerful. And then, of course, the static program structure is a source of absolute knowledge. And often, that static structure can be used to complement the incomplete nature of the dynamic and statistical methods, giving us a much more accurate view of how the software really behaves. The ultimate goal is for me to be able to fix bugs while I'm asleep. And if you think that's a good idea, I encourage you to join up. Go to this URL, and you can download instrumented versions of various open source packages. You can install them, run them, and every time you use them, you're helping us build a smarter system that can help software engineers find and fix more bugs. I'm happy to take a couple of brief questions before we move on to the next speaker.
As you point out, it's shipped with bugs. The developer or a developing organization, or I've seen some developing organizations that have a statistical model of how many bugs are left in the system after system test before they release the software.
Right.
Can you use some of your work to get some indication of how many bugs there are left in the system and track that figure with the passage of time?
We certainly can. Having an estimate of how many bugs are expected to still be present is exactly part of what we need to drive the Delta LDA system, that latent Dirichlet analysis. You actually don't say how many topics are reserved for bugs. You give a probability distribution. So you can say, I think there's probably about 10, there might be as much as 20. You give a sort of probability distribution, and then we fit the model to that. We can also determine whether that model is in agreement with your prior expectation or not. So if your estimates are systematically rather far off, our model will discover that. We can actually provide that as feedback as well.
I have a rather philosophical question. So when something crashes,
yes,
we usually see a pop-up window that says, okay, send a report to the vendor or don't send.
Right.
So in my experience, many people click don't send.
Right.
So I think there has to be we have to build a culture of sending those statistics to the vendor. So what's your take or experience in this issue?
Maybe it's because I'm the son of a political scientist, but I believe that if you don't vote, you get the government you deserve. And in the case of bugs, if you don't click send, then why should they fix your bug? They don't even know about it. I always click send because the way I see it, every time I send a failure report in, I'm voting in favor of that being an important bug. I want the users to be selfish. There's a sort of enlightened self-interest here. The more times you tell me about how the software is failing on your desktop, the more important your bug will look.
What do you do anything for privacy? I know there's been some recent work, including from Microsoft researchers trying to, provide these features without violating.
Yeah, that's definitely a concern. And actually, the sparse sampling that we do is part of our answer to that. That we learn very, very little from a single user. It's really all about scale.
Right, but the user has to trust it.
Well, you have a brilliant question,
right,
but it's going to be answered in a full half hour. Right. So we now have our next speaker, who is Galen Hunt. And Galen is going to, in fact, answer this by telling us what goes on inside that particular system where you click the button. And he has been at Microsoft for many years. He has, as he puts it, shipped many bugs in systems for Microsoft. I'm sure that's not true.
No, it's true.
And he also has more than 50 patents, which means that he has quite a nice little wall in his office of little patent blocks. And we're delighted to have you here with us today, Galen.
Thank you, Judith. I am not going to answer Luis's question, but you can ask it again when we come back. I want to give a couple of acknowledgments. So the paper, I'm going to actually be describing a paper that we presented at SOSP this year on the Windows error reporting system. And I had 8 co-authors on the paper. And I'm going to be very careful, a couple of disclaimers. I'm going to be very careful about how I use pronouns in this talk. When I use the pronoun we, it refers to these 8 individuals on this listed here and not me. In other words, so when I say, for example, we built this system, it means these 8 guys built the system, 8 men and women built the system, and I actually have had very little, I've only been involved with the project for about 2 years. And when I use the I, pronoun I as in I don't know, that means Galen Hunt doesn't have any idea, but these people actually probably do have a really good idea how to answer your question. So I don't know how to answer Luis's question yet. Next disclaimer that I want to give, well, as we've kind of alluded to already in this session, software has bugs. They've given me a different deck. Okay. Even shipping software has bugs, and even Microsoft software has bugs. And I'm actually going to point out, and Ed is going to go into quite a bit more detail in the next half hour, that, and so does your hardware. It has bugs as well, and we'll come back to that. So I'm going to be very careful defining a couple terms. First one is a bug. What do I mean by a bug? I mean a flaw in program logic. So for example, in this particular snippet of code, the programmer unintentionally randomly generates an address and writes to it. Now, very many people actually write this line of code, but effectively many people do produce that line of code. And the second thing is an error. An error is a failure in execution that is caused by a particular bug. So for example, if I run my program 5,000 times with this particular line of code, it's going to generate roughly 5,000 errors. Okay? And one correlation is, well, obviously one bug can cause many, many errors. And in the case of Microsoft, when you ship software to 1 billion users, we can generate many billions of errors. Okay? So the question we have is, if we're Microsoft, we ship code out to 1 billion users roughly, how do we know when things actually go wrong? Okay? And we want to fix when things go wrong, and we want to fix everything. We want to fix bugs regardless of their origin, whether they're bugs in applications or bugs in the operating system. We want to help fix bugs that are in software, hardware, and also bugs that are caused by malware. And we want to prioritize the bugs we fix as the bugs that are most important to users. And we want to create a generalized solution that is available to all programmers, not just Microsoft programmers. And when I say bugs, well, which ones do we care about catching? We care about all of them. Okay? We care about bugs that result in crashes, hangs, installation failures, invariant failures, etc. And the system that we build is this thing called Windows Error Reporting. And I'm sure everyone in this room has seen Windows Error Reporting. You've all been introduced to it, okay? And it appears you've been introduced to it with one of these 2 dialogues or something very similar. The top one is Vista and I think roughly what's in Windows 7. The one on the bottom is XP, okay? And this is the dialog box that pops up and says, hey, there's been a failure. Is it okay if we send some more information to Microsoft to help fix this bug? What I'm going to do today is explain what happens, what the system looks like behind that dialog box, okay? So first I want to introduce the system by some numbers. So billions. We collect billions of error reports every single year through Windows Error Reporting. We fixed thousands of bugs with WER, and it is used by Microsoft and over 700 other companies outside of Microsoft to fix their bugs. And the system is designed to be extremely scalable. Again, we have as many as 1 billion clients pushing data into the system, to the distributed system, but it is so scalable that in fact we only require 2 SQL servers to record every error that happens on every Windows machine in the world. Okay? And the last number 1, the number of programmers you need to access WER. In other words, how big does your company or your institution need to be in order for you to use WER? 1. Anybody in the world can get access to WER data for their application, okay, on their system. So I've given an introduction, the rest of the outline of the rest of the talk. I'm going to talk about how we process these billions of errors, and then I'm going to give some experiences of some of the unique bugs, the interesting bugs we've seen in terms of software, hardware, and malware, and then I'll conclude. Now, let's compare this with debugging in the small. So everybody, I assume everyone in the room here, we're mostly computer scientists, so most of you have written some program at some point in your life and given it to a user. So you give the program to the user hits some kind of bug, and they report to you, hey, I hit this bug, and you take their information, maybe you attach a debugger to their machine, and you find a fix for it, and you give them back a fix for that bug. Okay? It's a very simple process. It can take a lot of time, but it's relatively simple. Now imagine debugging in the large. Let's say you've got 1 million users instead of 1 user. Well, what happens in practice? What happens in practice is, at least what happened circa 1999 before we deployed Windows error reporting, is that the users would call up technical support. And they would tell a technical support, a technician would attempt to help them diagnose their error. And then infrequently, and actually in the case of Microsoft, it was roughly once a year, the technical support people would come to the product group and say, here's our top 10 issues that we're seeing from users. And then we'd try to take that and actually fix those bugs based on that error information. Little teeny drop, large amount of reports coming in, but little teeny drop that actually made it through to the programmers. And the fundamental problem here is, well, there's humans involved in the loop. Okay? One, we literally can't hire enough technicians to take support calls from every single time there's a failure on one of our systems. The data that we get through the support technicians is filtered by humans, so it's inherently inaccurate. It's hard to get additional data, so if we say, we need to drill down more, it's hard to get that additional data. We have no idea how prevalent an issue. We had no idea how prevalent an issue actually was. In fact, we used to describe that we debugged by decibel, which is the louder the customer was, the more likely it was that we'd fix their bug, regardless of how important that bug was in the general community, in the general population. And this technique was also completely useless for Heisenbugs. And so what we decided is we had to remove the humans from the loop. Although we will still use humans to fix the bugs. Okay? And so what we did is what we wanted to do is created a system where a single service that would allow us to track and record every error that occurred, whether application, OS, or hardware, on every Windows system worldwide. And with the belief that if we could measure what was really happening in the real world, we could fix it. And we could fix the bugs that were important. So let's make this a little more concrete. So assume that a developer has built a plugin for Outlook. And this plugin has a function that takes 2 arguments that runs within its execution. And if the first argument is odd, then it's going to randomly pick a word in memory and override it. Okay. What happens when you run it? Well, when that plugin gets deployed out into the world, users hit a crash. Windows error reporting pops up this dialog and says, do you want us to report this crash to Microsoft? The user hits yes, go ahead and send the information. At that point, we collect what's called a mini dump. It's basically a stack trace with, in addition to the stack trace, we collect a couple of pages of memory, part of the code around where the failure occurred, a small amount of additional data, and that mini dump is uploaded to the servers at Microsoft. The servers at Microsoft run a utility that we call Bang Analyze, and it takes that mini dump and attempts to diagnose and figure out diagnose the error into, we correlate the errors into what units we call buckets. It's a collection of error reports that we believe originate from the same source bug. Okay? And we keep track of how many error reports there are. And so the programmers then will say, this particular error report, the one in red, the bucket in red has 23, almost 24 million error reports. That seems like an important one to go debug. And so they'll pick that one out, and they'll go analyze that data to find and resolve the error. The Bang Analyze engine, it contains a bunch of bucketing heuristics. You can actually download this tool. It's part of the debugging tools for Windows. You can download it and actually run it on your own crashes on your own machine and look at that. And it encapsulates about 500 heuristics. The set grows roughly about we add roughly 1 heuristic per week. So to recap, what I've told you so far. Well, so the client software automatically collects a mini dump on a failure, sends the mini dump to the servers. We Bang Analyze tool buckets that error with similar reports. We increment the bucket count, and then developers prioritize their debugging effort based on the bucket counts, taking the buckets with the highest counts. Now, actually, that's not quite what happens because we optimize the system. So one of the things that happens is that most uploads involve nothing more than incrementing the bucket count. So in the case I showed before where there are nearly 24 million error reports, we don't send crash dumps for 24 million error reports. We send crash dumps for a few dozen error reports, and everybody else just says, yeah, me too. I had that exact same bug. Okay, but it gives us very realistic counts. In addition, the system allows developers to request further information. So for example, if they decide that a mini dump is not sufficient to debug an issue, they can ask for a full memory dump. Or they can ask for a memory dump and please collect these additional files as well. And the user's experience like that is they'll click the first send information, and then it'll come back and put another dialog box up and say, we'd like to collect this additional information. Is that okay with you as well? Okay. So the system is progressive. The system works by using bucketing strategies, and there's actually two forms of bucketing heuristics. There's a set that runs on the client side, and there's a set that runs on the servers. The client side heuristics are optimized for minimizing the server load. And so primarily we call them the labeling heuristics. Primarily what the labeling heuristics do is attempt, based on information available at the client, to decide where the failure occurred and identify that failure point uniquely enough that errors that came from the same bug are likely to hit in the same bucket, but not necessarily. And then when we get the reports onto the servers, we do additional analysis. We rebucket towards getting to the actual root cause. And so, for example, we start out on the client. We'll basically, the simplest form of bucket identity is a form of the program name, the binary, the version, and the PC offset within that binary where the failure occurred. And then when we get to the server, we will pull up symbolic information, so we'll convert that offset into a symbol, so we now know it's memcopy. We have other heuristics that look at things and say, oh, well, memcopy actually doesn't fail. It's someone else called memcopy with erroneous parameters, and so we walk back up the step and say, oh, who's the function that was calling memcopy? So that will get us down to, well, we now know it's the plugin, and it's the foo process within the plugin. And there's additional heuristics. There's quite a few of them, and there's more detail in the paper. Now, bucketing mostly works. It actually doesn't work all the time, and there's two ways that bucketing fails. And the first one is that a given bug, error reports caused by a single bug, can hit multiple buckets. And the easiest way to describe this is my example that I showed, the memcopy that's overriding a random word. There's a predominant bucket for this error, which will be when the generated address is an illegal memory address. It's not mapped into your address space, in which case you'll have an immediate failure that happens on that write. The second large set of buckets are where that address is a valid address in your memory, but the error is going to manifest itself sometime later on when you dereference whatever memory has been corrupted. Okay? Well, the problems with this is these generate extra server load because we do additional collection for the extra buckets, and we also must hand triage them. It's the only way we know to eliminate them. And we estimate that the upper bound on the number of these errors, these number of bugs that are incorrectly bucketed, is as many as 40% of our error reports. The other way that the system can fail in terms of not bucketing correctly is when multiple buckets hit one bug. And this, for example, if you have a routine and it looks like a single routine is causing the failure, but it's actually two separate routines. These are harder to isolate, makes it harder to isolate each bug, and we believe that these count for as many as 4% of our errors. Okay? So you may ask yourself, well, how can a system that erroneously accounts up to 44% of error reports, how can it possibly be useful? Well, the answer is scale. We have billions of error reports that come in a year. So what that means, you can throw away 100,000 here, throw away 100 million there, throw away another 100 million over there, and it really doesn't matter. You still end up with hundreds of millions of error reports, which is sufficient to drive the system extremely well. Okay. So I've talked about how we process the billions of error reports. Let's talk about some of the experience using the system. And what happens when developers go to the system and say, I want to analyze bug? Essentially, we get a graph like this. And this is from Microsoft Word 2010. when we did an early internal technical preview. It was a pre-beta of this, only to Microsoft users with inside Microsoft. And there's a couple of things you immediately notice. So what I've got across here is the top 20 buckets in terms of number of hits, and then the cumulative distribution function. And what you'll notice is the first 20 buckets account for over 50% of the error reports that were seen by users. Okay, the bucket curves follow a Pareto curve, and it has the beautiful thing about this is it means that if you fix these 20 bugs, 50% of your error reports immediately go away. Okay, so you've dramatically improved the customer experience by just fixing a small number of bugs, and that's actually the most valuable outcome of the system. So fixing a small number helps many, many users. Okay, and the system has been very effective in fixing bugs. One data point that we give is that when we first turned the system on in 1999, we found errors in bugs in the Windows kernel that had been in there for over 5 years, Heisenberg bugs that we'd never been able to isolate. But with Windows error reporting, by collecting billions of error reports, for any given bug, we collect enough instances that we can debug it, has been our practice. Another example of this is we had an antivirus vendor who had not been using Windows error reporting, and when they were not using it, they accounted for 7.5% of all of the kernel failures on Windows computers worldwide. In about 30 days, they fixed their top 20 buckets, and their account of the total Windows crashes was cut in half within 30 days. Okay, and you can use the system to fix your own bugs. I've actually used it to find bugs in my programs. Another class of bugs that we've addressed are hardware failures. And Ed, who's going to talk after me, will give you much more detail on types of failures and a lot more about the hardware. But this is a particular instance. This was a processor bug. I won't name the manufacturer. But we were seeing a large number of bugs, machine check failures coming from a particular hardware, from a particular class of processors. We went to the processor vendor and said, look, we think you have a bug. We're getting these error reports. The vendor said, we knew about that bug. We just didn't think anybody would ever actually hit it in practice. Well, what this is, in practice, people did hit it, and we knew how many people did hit it. On the day in red, day 0, they issued an update out through Windows Update that addressed this particular bug in their chips, and you see immediately the occurrence of errors drops down off to less than 20% of the failures of what we were hitting at peak. Okay. Now, so there's two important lessons. One of them is, hey, it actually can be used to find hardware failures, even though it was designed to collect software failures. The other one is that had this particular manufacturer been using the Word data and reading it before this, they would have found that bug a lot sooner than we did, okay, than was fixed otherwise. And we go out and use them as a poster child to convince other hardware manufacturers to adopt Word as well. And we've had great uptake with Windows error reporting from the failures. Other example of hardware bugs that we found, we had a really fun one. We had an SM BIOS, the system management BIOS in a particular laptop had the property that on resume from sleep, it would occasionally overwrite large stretches of memory with the name of the manufacturer of the laptop. Made it very easy to identify who was responsible for the bug. Another example, we found a motherboard USB controller that only implemented 31 out of 32 address bits. And so if your memory got mapped in above 2 gigabytes in the 2 to 4 gigabyte address range, that it would overwrite lower memory. And this one was a bit tricky to debug. What happened is we would just get these crashes. You'd have like a page of code with a blob that was, I don't remember how big the blob is, it was something like 128 bytes of blob of data written over it. And we passed it around for a while in Windows trying to figure out, did anybody have any idea what this 128 bytes of data was? Thank you. And somebody said, hey, this kind of looks like a USB packet. And it turned out that it was, in fact, a USB packet. We were able then, One of the things we collect in addition to the stat mini dump is a list of the hardware on the device. And so we were able to figure out that all these errors were coming from a particular hardware device. And we found lots of other ones, and Ed will talk about these in detail in his talk. The last thing I wanted to mention is we also use it for detecting malware. In this particular example is the Renos malware. This was, 2007 is when Renos came out. Renos was a social worm. It basically, you got a piece of email that looked like it was somebody you knew, and if you double-clicked the link, it actually made code run on your machine, and it would modify Windows so that after that, what happened is every time you logged on, as soon as you logged on, the machine would immediately crash. In fact, as soon as the login screen came up, and so the machine would just sit in this loop where it would come up to the login screen, crash, come up to the login screen, crash. And you can see by the peaks that we hit within 2 weeks of the worm going out on the internet that we were hitting over 1 million error reports per day. And one thing this demonstrates is the system is designed, it's far over provisioned so that we can tolerate these global events such as worms where many, many machines across the world send us error reports. The Blaster worm, when Blaster first came out, it was a 0-day exploit, and within a day, it accounted for over 10% of all the error reports that we were seeing in the Windows error reporting system. Okay, but one of the things is this notifies us that these errors exist. We often collect enough data that we can actually we can figure out what the exploit is, what they're doing, and then we issue updates. And in this case, the day in red is the day that the update went out through Windows Update to fix these machines. And one of the beautiful things this demonstrates is these machines were crashing. They were completely unuseful to users, but they were up long enough that we were able to get error reports up through WIR, so we knew that the error was happening, and they also stayed up long enough that we could dribble out the bits to do the Windows updates. And so what the average user would see is once they got infected, the machine would sit there and spin for a while, and then all of a sudden it gets a Windows update, and it's back, and everything's good. And that's the experience we're ultimately trying to get for, is we find your bugs automatically, and we fix them automatically. Get them out. The other paper, the SOSP paper has a much, much more detail on how we do the bucketing, the statistical debugging, the progressive data collection, and also the operating system changes we've made to make this all useful. The bullet points, the end conclusion. Windows error reporting is the first postmortem reporting system with automatic diagnosis. It's the largest client-server system in the world by installs, over 1 billion machines involved. It's helped us and over 700 other companies fix thousands of bugs and gotten rid of billions of error reports. And it's really fundamentally changed the way we do software development at Microsoft. As one vice president put it, Windows error reporting forced us to stop making bleep up. Okay? We know what's really happening, and so we're able to actually fix things. And there's also, you can find more out about it at this URL. Thank you very much. All right. Yeah.
Thanks, Bernard.
So do you guys collect information about healthy executions too from time to time? Like, does WIR, decide to?
So Windows error reporting does not report healthy executions. We have a new system that's come online with Vista, late in the Vista life cycle and Windows error reporting called SQUIM. I don't know what.
Customer Experience Improvement Program.
Yeah, it's a customer. You'll sometimes see the prompt saying, do you want to get involved in customer improvement? And that uploads information about healthy executions. Okay. Yeah, I guess you're precedent.
You mentioned that 44% of the reports are misbucketed.
Up to.
And I'm just wondering if you have done a systematic analysis of what characterizes those reports and what sort of bugs might be lurking.
The bulk of those, 40% of those, up to 40%, are what we call the heavy tail of the error reports. Okay, so these are buckets. There's this huge list of buckets that have very small numbers of reports. We think that many of those are memory corruption errors, where you've had some bug that's caused. We don't know. We're actually launching a research experiment this summer to try to figure out if we can get farther down in that. One interesting data point I'll give you is we have literally over 1 billion buckets that have one error report in them. Okay.
So you feel it is a long tail and there are humps out there?
It's a huge tail. There's got to be valuable information out there. We don't know how to mine it yet. And actually, we're very interested in input on how to do that.
I had a question about how you report errors back to customers or ISVs that we're capturing the crashes. You talked a little bit about the hardware manufacturers, but is there a mechanism where service providers or tools developers can register to get dumps as well?
Yes, so there actually is. At the WinQual URL that I specified, if you go there, you can actually register to receive dumps for your programs. And you basically upload information about which your programs are, and then we give you all the bucket information for your error reports. And like internal Microsoft developers, you can request additional data be collected, etc. It's a good way to describe it is all it takes is a simple signing of an agreement with Microsoft that basically says you won't do anything evil with that bug information. But yes, it's available to just about anyone. Race condition.
Perhaps I shouldn't use a microphone for this question. Do you have any data that you can tell us about how defect densities vary as a function of time?
Time over the life. You know what? I don't, but Brendan Murphy does. And so I'll point you to Brendan. Brendan has a lot of information about what happens over time with these.
Because one of the interesting things is presumably with the passage of time, the software becomes less buggy.
Yes, it does. Well, and one of the useful things we found is that, even the cases like where we have 2 bugs that hit the same bucket, well, when you fix one bug, its error accounts go away, and so then what you're left are the error accounts for the second bug, the hidden bug.
So who should I talk to?
Brendan Murphy.
Thank you.
He's at the Cambridge.
Yeah, he's at the Cambridge lab.
Or not upon here.
Yeah. Okay. I'll be available afterwards. Yeah, let's do one and then get on to Ed's
I was
talk.
just curious whether you guys are thinking about, how you do similar things for web applications. When you have code running on a browser, because you can do things like change, specific versions that you're sending to the user much more easily than talking about executables. So I'm just curious where you guys are going there.
So we actually we have instrumented versions. So I talked about Windows. So we have a Windows client. We also have Word clients in all of our Macintosh, our software that runs on Macintosh. We also have it in all of our JavaScript code that comes down from Bing and some of the other services. They actually have Windows error reporting clients, so they collect error reports and if there's a failure, and they'll send it up as well. The phones are instrumented as well. So we actually have quite a bit of instrumentation of how to try to help on those, and even in the web services as well. Okay.
Last question.
All right.
Last one. So about Heisenbugs, you talked about
yes.
Faults that cause many errors, but there are the faults that only very occasionally cause an error because of particular circumstances with respect to threads and state. Do you have any way to pick those up through this mechanism?
Well, we have a mechanism in that we at least collect those error reports, right? And so in the case of I mentioned there were some early bugs that we found in the Windows kernel. And those were ones where actually the error report came back as a failure in a particular line in the kernel code. And we actually, all of the failures that come back that look like they are actually in our kernel code, we send humans out to look at those failures. We don't wait for 1 million of those to accumulate before we go look at them, okay? And part of the heuristics, we have some things that help us prioritize buckets that look like they're very crucial pieces of codes, independent of how frequent they're hit. Okay. All right. Thank you.
Thanks very much. And now we have our third speaker, who is Ed Nightingale. And Ed is a researcher at Microsoft Research, and he is going to tell us about all the rest of it and how he does it on a hardware platform.
Thank you.
Thanks, Ed.
Good afternoon. So today I'm going to be telling you, looking at this error reporting data that we have and trying to get a better handle on how reliable hardware is out in the wild. So I'm going to start with an anecdote before I get into my statistics to convince you of unreliable hardware. And I've been here 2 years. When I was interviewing for a job, I had this interesting experience at universities where people in HPC started telling me about DRAM errors becoming more and more common in cluster computing. I was actually told about a notorious Department of Energy cluster that was not using ECC. And someone actually told me that they were taking their 6,000 machines and running it 3 times, taking 6,000 machines, running a 2,000 machine job 3 times, taking the best 2 out of 3. This sounded bad to me. But I thought this was very interesting. So, you know, when you interview, you have dinner. And I thought this was an interesting anecdote to bring up with other professors at the university I was interviewing at. And usually an operating systems professor or an architecture professor would say that's ridiculous. These memory errors do not exist. You have a sparse address space. It's large. If an alpha particle strikes, nobody's going to notice. There has to be something else going on. And I came to Microsoft and chatted with Vince Orgavan, and he said, you know, we see these all the time. We have a lot of data, and these problems do exist. So when I came to work here, we and John DeSuer started looking at these errors and started trying to understand, can we gain some insight into how reliable hardware is and where these failures are occurring? And I'll start just with the conclusion. You know, these hardware failures are non-trivial. We looked at 3 types of failures, which we'll get into in a moment. And the failure rate, after looking at about 500,000 machines over an 8-month period, was as high as 1 in 190 probability of failure. The recurrence of failures is also common. If you failed once, the likelihood of failing a second time from a hardware fault was up to an order of magnitude more probable. And these failures recurred frequently. So as many as 97% of the time, an operating system would crash from the same hardware fault within 10 days. And you know, things like your CPU speed actually matters. Not just in overclocking and underclocking, which we'll get to, but faster CPUs, regardless of their clocking rate, will crash more frequently than slower CPUs. And you know, we'll actually show that we can look at these DRAM faults and find spatial locality. So you know, the underlying point in this research is that, especially in systems research, we've often ignored the reliability of a single machine. We build distributed systems that are robust to hardware faults. But in a single machine, we simply crash. And I think there's an open question in area of research for building single systems that are robust to hardware faults. And the goal of this research is to demonstrate to you the frequency of these faults so we can start thinking about how to solve these problems. So I'm going to start with just talking about the methodology, and then we'll just get into all the different analysis. And I want to just make sure that we're on the same page in terms of terminology. Many of you are probably familiar with these terms, but just so there's any confusion, we're talking about failures versus faults. You know, a failure is an incident that occurs. It's just an operating system crashing. And a fault is a condition, it's a defect in a chip. Your failure might be recurring or non-recurring. And your fault in hardware can be permanent, like a burned out chip. It can be intermittent, where it happens every so often. Or it can be transient, where, for example, the infamous alpha particle strikes a transistor. So I'm going to talk about hardware faults in 3 very specific areas. Now, we have to do this because we have this data coming to us from end users' machines. We can't examine them. So we have to be very conservative about what we're declaring is a hardware fault so we can be certain that these aren't actually software errors. We're looking at CPU faults, disk subsystem errors, and corruption in DRAM. So for CPU, we're going to be looking at these machine check exceptions. Gail mentioned these. This is when an internal invariant is broken and the CPU throws up its hands and says, I cannot compute. It throws an exception and the operating system has to crash because it can't reason about the integrity of the data on the chip. So it can be caused by parity errors in ROM, parity errors in your L1 cache, errors communicating with other chips on the motherboard, bus errors, it can be manufacturing defects, it can be caused by stress or heat, underpowered, overpowered, dust, dirt, anything you can think about. Second set of failures we're going to talk about are disk subsystem failures. We're talking about disk subsystem failure. It's when there's a failure to read data in a critical kernel code page. For example, reading from the page file. This is my favorite picture. That's the IBM's first 5 megabyte hard drive. I think it weighed a ton. You can see the bits on it. So you know, what's interesting about this failure is the dump driver eventually has to write data to disk. And you know, it's unclear where these failures come from, but we see them all the time. They can be a faulty bus controller. They can be buggy firmware. loose cables, heat, or vibrations, faults in the platters or in the disk mechanism. What ends up happening is you can't read this data. You repeatedly try to. The operating system has to crash. Finally, the other type of failure we're going to be looking at is a 1-bit error in a kernel code page. So we can diagnose this fault as when the mini-dump comes into Microsoft, we get the 256 bytes around the instruction pointer. We can do a diff of the code with the correct code, and we can see that 1 bit has changed, causing the instruction pointer to go off the rails into somewhere else into the kernel and causing an exception and a crash. So these are only kernel code pages. So we've got the MMU to protect us from stray writes from other pieces of software. It's possible that it could be a DMA, but improbable. And I have a longer discussion about that. But since DMAs are typically byte-sized, not bit-sized. So these are, this is a very small portion of your address space that we're measuring. And there are 2 data sets that we're going to be looking at. One is called OCA, or Atlas, which is what Galen mentioned, where we get these hardware dumps. We don't have any information in the absence of failures, because this is only reporting on crashes. And the second data set is called RAC. RAC are machines that have voluntarily decided to report all of their usage data to Microsoft. They anonymously report to Microsoft every 2 to 4 days about all of their uptime. So we get all the events that are reported, including the absence of failures, which means we can do a reasonable statistical analysis about how reliable these machines are. We captured about a pool of 1 million machines over the period of 8 months. So how frequent are these failures? This is a big table, and I'm going to walk you through it. On the left column, we've got the different types of faults, different types of failures caused by these 3 types of faults that I mentioned. The second column, I have something called TACT. TACT stands for the total accumulated CPU time the machine's been running. You can imagine that a machine's turning itself on and off while it's been reporting to Microsoft. And so what we're looking for is a minimum CPU time of 5 days or 30 days while it's been executing. So 5 days of CPU time could be far more calendar time that the machine's been reporting to Microsoft. The third column here is the probability that a machine is going to crash over this 8-month period due to one of these failures, one of these faults. So you can see, for CPU machine check exceptions, the probability of failing is as high as 1 in 190. For a DRAM 1-bit error in the 30 megabytes of your kernel's address space, the probability of failure is as high as 1 in 1700. That might seem like a high probability to you, but compared to what we typically do to measure DRAM faults, which is failures in time, FITS, which is failures per billion hours of operation, this is a very high failure rate. And then example disk subsystems as well, it's 100 to 270. The second thing you'll notice in the next column is this is the conditional probability of failure. How likely is a machine going to crash a second time given that it's failed once already? And you can see the probability of failing a second time is up to an order of magnitude more likely, or 2 orders of magnitude more likely. So what this is telling is that once you're in this failure-prone population, you're going to continue to stay there. Your probability of failure is going to continue. You have a very high probability of continuing to suffer failures from these different types of hardware faults. You see in the last column, there's a probability of a third failure given you've failed twice before is also quite high. And below this table, we've got the recurrence rate. So we looked at how likely is it that once a machine has crashed once, it will crash a second time within 10 days, within 30 days of that first failure. And for example, with the CPU subsystem, 84% of the machines that crashed once crashed a second time within 10 days. With a 1-bit DRAM failure, 100% of the machines that crashed once crashed a second time from a single bit error in a kernel code page within 30 days. So these aren't rare. They don't appear to be transient. They're recurrent. And they're affecting a lot of people. So if we go down the rabbit hole, we actually looked at, we've got these DRAM faults. We can do a more specific analysis. We can do a spatial analysis and see if there's any correlation between where these failures are occurring. So we took 300,000 1-bit errors out of Atlas, which is the database Galen mentioned. And of the machine that crashed more than once from a single bit error, 79% of them crashed at the same physical address with the same bit flipped. So these are not alpha particles. These are defects in the chips. And we're seeing these defects in the wild. Consumer machines are not going to have ECC memory anytime soon because people don't want to pay for it. It's a premium part that our OEM partners use to differentiate their offerings. And unreliable hardware is a reality that we need to address, and we're not doing a very good job of it in the operating system. So let's look at some more broad categories of failures and see if we can gain some new insight into what types of machines are seeing these types of crashes. The first thing I want to do is talk about overclocking. And just for those of you who are not familiar, I've got a brief primer here. When Intel has a big wafer of CPUs, they start testing all the CPUs on the wafer, and they start lowering the clock frequency down until they find the frequency for each chip on the wafer where it passes all of their tests. This is called the binned or the rated speed, and then that's what they sell it at. Now, it's not quite at the rated speed. For example, your 2 gigahertz CPU might run at 1995 megahertz because that's the frequency or pass test. So when we're classifying machines, if it's below that rated speed that it's sold at, which we can diagnose in the dump, it's considered underclocked, which some machines can be naturally underclocked. If it's within 0.5% of the rated speed, we're going to call it rated. We're going to toss out these machines between 0.5% and 5% because we can't be sure what's going on there. If it's above 5%, we're going to declare that machine's been overclocked by the user or by the company that's selling the chip.
You mean 0.5%, not 0.05?
No, 0.05.
0.05?
Yes, very conservative. Yeah, when you get a chip from Intel, it's not going to run very much above the rated speed unless you've overclocked it. So that's 0.05%. So what happens with overclocking? Well, we took the chips from 2 major CPU vendors and measured the rate of failure when you have overclocked. As you can see, with these 2 vendors, the probability of the first failure increases dramatically if you're running an overclocked chip when it comes to machine check exceptions. And the same is true for 1-bit errors and disk subsystem faults. So this has been something that I'm seeing a lot of people have assumed. If you overclock your chip, you're probably going to run into failures and faults because you're running a chip at a speed where it hasn't passed test at the manufacturing facility. But more interestingly is that we measured the effects of underclocking on these machines. What happens when you look at the chips that are sold that are running under their rated speed? And it turns out that these underclocked machines are up to 80% less likely to crash when they're running a little bit slower. So, especially with the machine check exception with DRAM faults, you're far less likely to fail if you have a chip that's underclocked rather than running at rated speed. This is throwing out overclocked chips completely. Disk subsystem faults seem the least benefit, but they're all statistically significant. So what's causing this? We're not sure. I'll answer questions at the end if you don't mind. We're not really sure where this boon in reliability is coming from, but you can think about the fact that we underclock machines now for power, but it also might be want to underclock these machines for reliability. So the next thing we looked at is the infamous white box machine, or you might call them generic machines. People build out their own box at a local electronics store, and they run them. And what we were able to do is we took the top 20 OEMs by sales volume worldwide and declared those brand name machines, and then we took everything else, declared those to be white box machines, or machines that are custom built, and looked at the reliability of them. And you can see, interestingly, that these brand name machines are far more reliable than the white box machines across the board in the large. So this might not be surprising to some of you. When some people put together their own machines, they might exhibit errors, but also you tend to see that the brand name machines tend to be, if you look at the types of motherboards they produce, they tend to be a little bit better built, so they're running a little bit better, more reliable. The next thing we wanted to look at, there's a typo, is desktops versus laptops. And we had some surprising results here as well. Across the board, laptops end up being more reliable than desktop machines. You might have assumed that your laptops would be far less reliable, and we're going to see many more failures because they're jostled, they're bumped, they're thrown, you get coffee spilled on them or whatever. But in reality, your desktops tend to be less reliable than the laptops. And one of the interesting things is that the manufacturers of disks and of laptops themselves have spent a lot of money and a lot of effort to make these machines robust to failures, to being shaken, to being dropped. But they haven't put a lot of that engineering into a desktop machine. So you bump your knee against your desktop machine or vacuum cleaner, whatever, and the disk wobbles. There's no protection there for being robust to failures. So you're going to end up getting a fault. But all those protections are built into laptops. So the next thing I want to look at are these machine characteristics. And to go a little bit further down the rabbit hole, when you look at all the machines in our study, it's very difficult to compare them directly in terms of the amount of how long they've been running. So we're using something here called a PP plot. For those of you who aren't familiar with PP plot, it's a comparison of 2 CDFs. So in this case, you take the CDFs of the failures you're looking at compared to what you're studying. In this case, we're looking at CPU speed. And you compare that to a CDF of your TACT, or your accumulated CPU time against what you're studying. What this tells you is that if the problem you're looking at, so CPU speed, is completely independent of failures, you're going to get a line that looks like, you're going to get a line that is, that fits within, matches the black line. Basically, there's going to be no correlation. However, if you don't get that, you're going to see that there is a correlation between what you're studying and the types of failures that you're measuring. So this is a way of taking the fact that in our study, we have machines that have different amounts of uptime. We have machines with different numbers of failures and allowing them to take those into account and measure these types of failures. So in this case, we've got what's the effect of machine speed. This isn't talking about overclocking or underclocking. It's just saying if I have a faster CPU, am I more likely to see a failure? And if you look at this compared to accumulated CPU time, we see that this is the case. If you have faster CPUs, especially when it comes to DRAM failures and CPU failures, you're more likely to crash than if I have a slower CPU. Now, you realize there's one thing we're not taking into account is we're not taking into account the fact that faster CPUs are going to execute more cycles per second than slower CPUs, which might account for the skew. And indeed, if you take that into account and you compare it to total accumulated cycles rather than seconds, you see that most of this correlation disappears. And so for any given cycle, every CPU is equally likely to fail. But there's another insight here, which says that because you run a faster CPU and you're executing more cycles per second, for any given time period, faster CPUs are more likely to fail than slower CPUs. So if you're worried about reliability in the large, you'd like to find the slowest CPU, perhaps, that can run the workload you're interested in, which means you'll be less likely to see failures within the given lifetime of a machine. Now I'm going to, wonderful. That was taking a long time to render before. So the next thing we look at here is this overclocking, underclocking ratio, which I talked about earlier. And this is another way graphically to confirm the results that we had before. There's a lot going on in this graph, but just to walk you through it, again, we're looking at CPU failures, DRAM failures, and disk failures. And these areas with the dotted lines tell you R is less than 1. This is the ratio of your CPU speed compared to the rated speed. So less than 1 is underclocked, equal to 1 is rated. Between 1 and 1.05 is this unknown area, though we're measuring it here. And then greater than 1.05 is strictly overclocked. And you can see with CPU failures that there's this huge positive correlation and swing at the top that says that the higher your machine is overclocked, the far greater the probability that you're going to suffer a crash. And we can see the same correlation, although less pronounced, with DRAM failures as well. Now with disk failures, you can see that it kind of approaches unity at the top, and so there isn't that same correlation there. But and at the bottom end, you can also see that underclocked machines are far less likely to fail. So we're confirming the earlier result, but also giving you kind of the entire distribution. So you can see how much more likely it increases as you overclock your machine. So the last thing I'm just going to present here, and there's this work is in submission somewhere, so there are more results, but I don't have a paper to reference you to just yet, is the effect of calendar age. And so we actually looked at the biostate of the machine and then measured the CPU failures, DRAM failures, and disk failures. What we found, interestingly, is that there's a positive correlation with CPU failures and DRAM failures, which says that younger CPUs and DRAM on younger machines are more likely to fail. There's a negative correlation with disk failures, which says that older disks are more likely to fail in this system. So this might say that disks have a better burn-in than CPUs and DRAM. We're not sure. We're just hypothesizing. But I think this is a very interesting result. The last thing I wanted to touch on is trying to understand what the actual intermittent failure rate is. So earlier we said, it looks like that a lot of these failures are not transient, but JD actually did a statistical analysis to see if we could get a handle on what the actual intermittent failure rate is. So if you look at the number of failures, the recurring failures are greater than the non-recurring failures. But if you look at a count of machines, there are fewer recurring than non-recurring. And so if we just measure this, we can see that, for example, 30% of failing machines show recurrence for CPU subsystem faults. But this non-recurrence rate doesn't imply transience. The reason is that we have a window of time that we're measuring these machines, and a machine might fail before we measure it or afterwards. So just because we see a single failure while we're measuring it does not mean that the machine is not seeing recurring failures. So we're able to do a temporal analysis and develop an analytical model that allows us to estimate what the actual recurrence rate is. And so by doing this, we're able to see that the actual estimate of the likelihoods are up to 40% of CPU subsystem faults are intermittent, disk intermittence faults are up to 39% as well. And DRAM, up to 19% of these faulty machines are intermittent. Sorry, I lost my train of thought. But what this shows you is that we do have a significant intermittent fault rate. And what's interesting about this analysis is this is not the fault rate in hardware. This is the measured failure rate of the operating system crashing. This is something else that we haven't seen before. We've seen a lot of measurements of how often hardware might be faulty. This is actually showing you how often faulty hardware impacts operating system reliability. So just as a conclusion, these first failure rates are non-trivial for machines out in the wild. These recurrent failures are common, and they happen quickly. Things like attributes such as CPU speed do matter. And the DRAM faults we're seeing have spatial locality, which suggests we're seeing actual hardware, faulty hardware out in the wild. And the configuration of your machine matters. Brand new machines tend to be more reliable than generic machines. Laptops tend to be more reliable than desktops. Machines, oh, and yeah, there's another study we didn't put up there. Machines with more DRAM will suffer more bit errors and CPU errors, with fewer disk failures. So that's the study. Thank you very much.
Thank you for that fascinating talk, Ed. Questions now? Yep, well, right here.
Well, I'll start with a comment. So I think you made a pretty strong case that processor manufacturers being kind of greedy when they bin their processors. Right? They're probably binning in a rated for higher frequencies so they can charge more money for it, when in fact, they should have not have been as aggressive, I guess.
I don't know.
But yeah, you work for Microsoft, you can say that. But I think that's...
I really don't know.
But so the other thing I was curious about is that I would imagine there are a lot of hardware failures that do not generate these events. Like you can imagine, say, a bit flip on a register that would just generate some computation that's going to lead to bad results, going to lead to software crash that has no apparent software explanation.
Oh, absolutely. And this is just the kernel. These are just kernel failures.
Right, exactly. And things that generate very specific events. So it would be interesting to think about methodologies that allow you to identify that an error must have happened by a bad computation as opposed to something wrong in your software, right? And because they're classic, costly hardware bugs like the floating point error, right, where there's no event, a clear event is going to generate
Sure,
that.
Absolutely.
A very nice study. Thank you.
Thank you.
Tom at the back there.
Oh, what happens with flash memory?
Flash disks?
Yeah, flash disks, sorry.
When we did this study, there were very few of them out in the market. And so we didn't do any sort of analysis related to SSDs. So I'm not sure. I don't know. That's a good question, but I can't answer it. So.
Did you do any analysis of server class or data center machines?
I did not. These are the vast majority. I mean, there might be a few in here, but the vast majority of them are all running consumer Windows. These are all consumer machines. So server machines are going to be running. They're more expensive. They're probably running ECC memory. They might have higher quality disks. I don't know. So, but I'd just be speculating. So.
This is a really fantastic window into this sort of hidden world that we usually don't even get to see. You showed that OEM manufactured equipment is more reliable than non-OEM manufactured equipment with that sort of top 20 cutoff. Is there anything interesting that you can tell us about what's going on within that top 20?
No.
Who are you buying your next PC from?
Not without a lot of NDAs. No, I can't share any. No. I can tell you that Microsoft worked closely with the OEMs so that they have information about how reliable their models are. And that's important to them, to try and encourage them, just as Galen mentioned, encouraging companies to be involved with Windows Error reporting so their software is more reliable. All the OEMs are deeply involved in figuring out how reliable their models are, to try and figure out what there's batch problems or other problems out in the wild. So,
thank you.
Sure. Yes. You can just shout it.
Variant on that question.
A variant on that question without revealing the names of the OEMs. What was the extent of the variance within that population of machines?
There was variance.
How wide was the?
I don't know. Where's Vince? I have to ask him.
Have you done any experiments with the room and CPU temperature?
We'd love to, but that data, a lot of the data ends up being chipset specific, so it's difficult. So there's actually a lot of pieces of data in the hardware that could be very revealing. In addition, for example, CPU temperature, on every DIMM, there's actually a manufacturer date and the location of manufacturer and the brand. And that is something we can't get access to because the BIOS would have to raise it up in terms of the tables the operating system has access to. CPU, that's chipset specific, which means Microsoft would have to support 1,000 chipsets in the operating system to query it, while the BIOS just supports it once. And so we don't have the manpower to implement that. We have to basically try and convince the OEMs to say, this is really important to us. Could you raise this up to a level where we could capture it and report it? And we don't have easy access to it. This changes over time, but it takes a long time to get access to the data.
Great. Okay. Well, I think we're going to call that off and say thank you very much